Hi, thanks for joining me today. I've got a fun infinite series problem. We want to know, does the sum from n equals 1 to infinity of the fractional part of n times the square root of 2024 converge or diverge? So what does this fractional part mean? Well, the formal definition is it's x minus the floor of x. But what does this basically mean? It's just the bit after the decimal point. So if I have the fractional part of 3.14, that's just going to be 0.14. If I have the fractional part of 8, that would just be 0 because 8 is an integer. So this is what the fractional part is, and we want to know if I compute this infinite sum here, would it converge or would it diverge? If you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so what we're going to first do is prove an inequality based off the summand. So the fractional part of n times the square root of 2024. Well, this just by definition is just n times root 2024 minus the floor of n root 2024, like so. Okay, and now what we're going to do is kind of multiply the top and bottom of this imaginary fraction. If I put a divide by 1 here, by the conjugate of this guy. And so this is going to be n root 2024 minus the floor of n root 2024, floored, times n root 2024 plus the floor of n root 2024, like so, and then all divided by this fraction here. So n root 2024 plus the floor of n root 2024, all floored. Okay, cool. Why have I done this? Well, basically because the numerator then just becomes the difference of two squares. So this will be 2024 n squared minus the floor of n root 2024 all squared, like that. And then our denominator is just this guy here. Well, what can I say about this? Well, this thing here is going to be less than or equal to this thing here. So this denominator here is less than or equal to two lots of this thing here. But since it's in the denominator, I can say that this thing here would be bigger than or equal to two lots of n root 2024, like that. Okay, now what can I say about this? And now here's where this is a pretty nice argument. This numerator here, we can say with confidence is definitely going to be an integer, because this part here is definitely an integer. This part here, well, the thing inside the square brackets is an integer. When I square it, it's still an integer, so the numerator is definitely an integer. Furthermore, it's definitely going to be non-negative. Why is that? Well, that's because this thing is definitely bigger than or equal to this thing. And this guy here is the square of that, and this guy here is the square of that. So this thing must be bigger than or equal to this thing. So we know the numerator is a non-negative integer, but furthermore, we can actually say it must be a strictly positive integer. Why is that? Well, it can't be 0. Why can the numerator here not be 0? Here's why. Let's just call this thing inside the brackets here t, and t is just some integer, depending on what n is. And suppose this numerator was 0, then I get 2024 n squared equals t squared. But then if I rearrange this, I get root 2024 is just t over n. But then this would mean that 2024, or the square root of 2024, was rational. And root 2024 is not a rational number because 2024 is not a square number. And so this means that our numerator here is a non-negative integer, but it can't be 0, and so therefore must be strictly positive, so it must be at least 1. And so this guy here is at least 1 over 2n root 2024, like so. And perhaps you can see where I'm going with this. So what have we shown? We've shown that the fractional part of n times the square root of 2024 must be at least 1 over 2n times the square root of 2024. But that tells us that this sum that we're trying to work out must be at least the sum from n equals 1 to infinity of 1 over 2n root 2024. But this is essentially just the harmonic series, which diverges to infinity pretty famously. It diverges very slowly, but it definitely does diverge. And so therefore that means, by comparison, this guy here must also diverge. And that is our proof complete. So a really nice problem, and I think a really interesting way of attacking it. We used the fact that 2024, or the square root of 2024 is irrational in order to prove that this infinite sum here diverges. And it didn't take or require that, any advanced tests or anything like that, which I think is quite nice. Anyway, we'll finish off there for today. If you have enjoyed this video, please do give it a like and subscribe if you haven't already. Thanks for watching. I'll catch you in the next one. Have a great day.